Okay, so I had another abrupt end to that last video. I realized what was going on. My recording device is my phone, and I ran out of space, so my video just stopped itself. That's okay. I cleared some space off, and we should be good now. So let's go ahead and pick up where we left off. What we had done is we had created a phase portrait, and we're trying to kind of look at what a solution curve passing through a particular point might look like for this DE that we were given. I had given this point down here in this region that we were calling R1, called it X naught, Y naught, and then I was saying, what would a curve that passes through that point look like, roughly speaking? Our phase portrait over here says that on that interval, we have a positive derivative, which means our function should be increasing that entire time. And so I started sketching a curve, and I think the video cut off before I started sketching this. But I started sketching this curve. It's increasing, and it passes through that point. Now, would this curve continue on kind of indefinitely upwards? Well, the answer is no, because remember, we have these equilibrium solutions here, and these equilibrium solutions are given kind of as parts of a slope field. So even though our curve is in the way that I'm drawing it appears to be increasing in slope, it can't just pass through this equilibrium solution here, because the slope is going to guide that thing kind of as a horizontal asymptote. You're going to see this kind of behavior happen here, like that. Okay, so not only is this solution curve going to be increasing in this entire region, but it's also not going to be able to escape this region. It's going to be bounded above by that equilibrium solution y equals 1. Interesting. Okay, now what can we say about a solution curve in this second region here, R2? Let's pick another point and think of that as a different x naught, y naught. In this region, in R2, where y is between 1 and 3, we have a negative derivative, which means that we have a decreasing function. And by the same reasoning here, the curve has to be decreasing. It has to pass through that point, and it's going to be completely trapped between these two equilibrium solutions. So we're going to end up with something that looks maybe like this. Okay? Notice that it's treating those two equilibrium solutions as if they were horizontal asymptotes. It's approaching them, but it can't cross them. Okay? And then finally, let's suppose that we have a point in this third region up here, x naught, y naught. In that area, we know from our phase portrait that our function should be increasing. And so I'm going to sketch an increasing curve that passes through that point. Okay? Now, I don't know if I got the shape of these curves correct, but I do know just that little bit of information. I do know whether they're increasing or decreasing, and I do know that they're bounded by our equilibrium solutions. That's useful information even if we don't have an explicit solution to work with. Okay? All right. So, on that topic, I mentioned that those equilibrium solutions are acting as horizontal asymptotes. In those cases, we would call the critical. Sorry, let me back that up. What is a horizontal asymptote? Well, in the graph of a function, a horizontal asymptote is telling you what value a function is approaching as x approaches either positive infinity or negative infinity. Now, in the case of differential equations, we're typically mostly just interested in what happens as the independent variable goes towards infinity when we're interested in the long-term behavior of the system that the DE is describing. So in the case of those applications we talked about, where the independent variable was time, if you're interested in the long-term behavior of that system or that physical phenomenon, then you're looking at what's happening as t approaches infinity. Is it just shooting off towards positive or negative infinity, or are you approaching some finite number, in which case you're looking at a horizontal asymptote for your solution curve. So back here, we noticed some, by sketching these possible solution curves, we noticed that y equals 1 and y equals 3, our two equilibrium solutions, are acting as horizontal asymptotes for some of these curves. Now let's look at the curve equilibrium solution y equals 1. What's happening to my solution curves as x approaches infinity? Well, this curve down below is approaching my equilibrium solution, and this curve up above is also approaching that equilibrium solution. Both of them are approaching 1 as x goes to infinity. And given the way that we kind of worked through this, we would expect any solution curve lying in either of these regions to do the same thing. For that reason, in this case, for this differential equation, we call the critical point 1 an attractor. And what that means is that as x approaches infinity, these curves are being pulled toward that equilibrium solution. It's attracting those curves, those solution curves. Okay? If a critical number is an attractor, we oftentimes also describe it as asymptotically stable, meaning that it's playing the role of a horizontal asymptote in the graphs of those solution curves. Okay? Compare that to this equilibrium solution up here. So when we had y equals 3, what's happening to the solution curves that are near that equilibrium solution? Well, as x approaches infinity, these curves are moving away from that horizontal line. They're not moving towards it like we saw here. They're moving away. And so for that, we would say that the critical number 3 is not an attractor, it's a repeller. A repeller meaning it's repelling these curves, pushing them away from that equilibrium solution. We also describe those types of critical numbers as asymptotically unstable. It's not, even though it's a horizontal line that plays an important role here, it's not acting like a horizontal asymptote as x approaches infinity. It appears as though it is as x approaches negative infinity, but we tend to not really care about that. Okay? So I described that here, I give those definitions here, and I use some limit notation and stuff like that, but that's intuitively what's going on. Now, it's possible for a critical number for an autonomous differential equation to be neither asymptotically stable nor unstable. And even though that's not appearing here, a way of imagining that is suppose that I knew my function was increasing on this region as well as this region between 1 and 3. This curve below my equilibrium solution y equals 1 is approaching that horizontal asymptote, but a curve in this region, because it's increasing, would be moving away from it. So some curves might move toward that equilibrium solution, others might move away, and in those cases we can't say that it's stable or unstable. We call that semi-stable. Okay? So I want to do another example where we're looking for critical numbers or critical points in an autonomous DE and classifying them according to their asymptotic stability. So this is the DE that we're working with. dy dx equals y times y minus 2 quantity squared times y plus 1. And we want to classify each of the critical points that we find as asymptotically stable, unstable, or semi-stable. I'm going to create a phase portrait for this one and see what we find. Okay, so here's my phase portrait. This is the y-axis. I can see from this function, because it's conveniently factored already, that the zeros of this slope function would be 0, 2, and -1. So I'm going to put those here. -1, 0, 2. And remember, what that does for us is it creates 4 subintervals that we can look at. -infinity to -1, -1 to 0, 0 to 2, and then 2 to infinity. Okay? All right. And we determine the sign of our slope function by picking sample points within each of these intervals, plugging them into the slope function, and then just thinking about the sign of that slope function. Okay? Or the sign of that output. Now, while I'm doing this, notice I have this y minus 2 quantity squared. What that means is that no matter what sample point I choose from these intervals and plug in here, after squaring this part, it's going to come out positive. So that doesn't really play any important role. What's going to matter are the factors y and y plus 1, because those can come out either positive or negative depending on what I plug in for y. So over here, I'm going to plug in a sample point. Let's plug in negative 100. That's a number that's in this interval. This would be negative, plugging it in for y, and negative 100 plus 1 is also negative. So I have negative times negative, which is positive. We already know that's going to be positive. The whole thing comes out positive. What about here? Negative 1 to 0. Let's pick something in between. How about negative 1/2? Okay, ignore this factor. We already know it's positive. If I plug a negative 1/2 in here for y, that's a negative. Negative 1/2 plus 1 is positive 1/2, and so negative times positive is negative. We have a negative there. Okay, now on to this interval from 0 to 2. We're going to plug in something in between 0 and 2. How about 1? I have a positive